So welcome back to another video. So in today's video we have the following limit. This limit is actually a perfect example when you're learning the introduction of indeterminate forms in a Calculus 1 class. Here we have the limit as x approaches 0 from the right of x to the negative x power. So there's actually 7 types of indeterminate forms. You have one with 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus infinity, 1 to the infinity power, infinity to the 0 power, and then 0 to the 0 power. So as you can see, if you were to plug in the values for here, then you know that we're going to get one of the 7 forms. So in today's video, it's just basically just rewriting the limit and seeing an example of how indeterminate forms work, using that to the point where we can actually apply L'Hopital's rule, which says that if you have 2 of the indeterminate forms, 0 over 0 or infinity over infinity, then you can actually take your functions from both the rational function, specifically from the numerator and denominator. You can take its derivative, then evaluate the limits, determine if it's still an indeterminate form, then apply the same method until you get some finite value when you take that limit again. So right after evaluating the value, there's also one thing I want to discuss. It's also with a previous remark from the last video I uploaded, but we'll get to that eventually when that time comes. So anyway, let's actually just jump right in. Obviously, we see that if we plug the limit, so if I just write the same thing, we see that if we plug this, we have 0 and then to the power negative 0, in other words 0 over 0, so that hence we have an indeterminate form, right? But you can't really use L'Hopital's rule in this sense because it's actually just a polynomial function. So, and L'Hopital's rule applies to rational functions. So what can we do to rewrite this? Well, to make things a little simpler before we approach that, let's actually rewrite our limit. We can actually using our rules of like natural logs into e base. So we write this as e to the power ln of x to the negative x. Then rewrite that using the rules of natural logs to move the negative x in front of our natural log. So this is e, then multiplied with negative x, then times ln of x. Then applying with the rules of continuity, we can say that we can write that as e to the power the limit as x approaches 0 from the right of. Then since it's a negative, so I'll just move that negative outside, that's a constant, so it's just x, and then times ln of x. Really, we just need to focus on evaluating our limit. The limit as x approaches 0 plus of x and then ln of x. What you'll notice, you plug 0 for our function, so we have a 0, then multiply with a, so ln of 0 does not, is undefined, but if you take the limit from the right, from 0 of the right side, you'll notice that it actually just, it approaches negative infinity, hence we have a indeterminate form of a 0 times infinity form. So what can we do? Let's actually rewrite this in a way that we can write it as a rational function. So entailing that if we were to take that limit again after that rewritten expression, so what I'll say is that we have ln of x as the numerator, and then I can write x from here as 1 divided by x in the denominator. Then you'll notice if we were to plug 0 from the right back in again, so we have a negative infinity, and then over here plug 0 from the right, this is approaching towards infinity, so hence we have a infinity over infinity indeterminate form. Then by applying L'Hopital's rule, we can take the derivative of both the numerator and denominator and take that limit again. So here we have ln of x is just 1 over x, and then from the denominator this is just negative 1 divided by x squared. Do a little bit of rewriting, so we have 1 over x multiplied by, flip the reciprocal, so negative x squared, and then divide by 1. So hence we have that this is the limit as x approaches 0 plus of negative x, which indeed is equal to 0. So now if I just take what we just evaluated, so over here we say that this is 0. Then if I just go back to here, then we have e, and then to the negative, plug in our limit that we just evaluated, which is just 0, and hence this is just equal to 1, like so. Alright, and there we have it, the final answer of our limit with the whole analysis of indeterminate forms with the limits. Now time to bring up the other discussion. So in the last video I uploaded, which was, the integral from the cotangent of x, natural log of secant x dx, there was actually part of the step that one of the users actually commented on, and specifically this is the step where we were dealing with after applying the integration by parts after applying the whole geometric series. But if you haven't seen that video, I advise you do. It's actually pretty interesting, so I'll leave that in the link in the description below. Or it's actually in the end cards in this video, since I usually link them to the previous videos of every upload I make. So either one's your choice as a viewer, however you want to navigate through. One of the steps was that we have, after applying integration by parts from one of our, rewritten integrals, so we have that the following was ln of t, then multiply with t to the power 2n plus 2, and then we divide this by 2n plus 2. Now obviously that we had a bounds from 0 to 1, but if you plug 1, then the whole thing becomes 0. But if we were to plug this at t, so you'll notice that if you saw the video that I actually made an argument by saying if I just plug 0 here, then the whole thing becomes 0, which that's not likely the case. Or it's not the case, not likely, it's likely not the case that if you plug 0 over here, you have a ln of 0, which is undefined. If you take that as a form of a limit, then that actually approaches negative infinity. So we have a indeterminate form. So really now let's fixing that discrepancy and actually rewrite this, or not rewrite it, but actually reevaluate it so that we get the result is equal to 0 rather than following with the argument I made from the previous video. So if we write this as a limit, then the limit as t approaches 0 from the right of ln of t, then multiply with t, 2n plus 2, then divided by 2n plus 2. Then what I can do is 2n plus 2, the n does not depend on the limit for the variable t, so I'll just move that outside of our limit. So 2n plus 2, then limit t approaches 0 plus of ln of t times t to the 2n plus 2, like so. Now from there, now you'll notice is that we just had to evaluate the limit instead. So I'll just rewrite the same thing again. Then if you plug 0 right from over here, you'll get that this is just a negative infinity multiplied by 0 indeterminate form. So you're thinking to yourself, how can we rewrite this? Well, we just applied, this is a similar example of what we just did for the limit we were given. This is why I wanted to bring this up, since it's actually a very good transition to understanding on, like, you can't say just because it's 0 because you haven't really discussed about what the natural log of some undefined number would do in that scenario. So this is a good thing I brought this up. Thank you for commenting on that error. So if I just rewrite this in a way that eventually we can actually apply L'Hopital's rule, so I'll do the same thing, ln of t in the numerator, then this will be 1 divided by t to the power 2n plus 2. Okay, so now if I just plug the 0 in, so we have a negative infinity, then over here this is actually 0 for the right, so it's actually approaching positive infinity, so a indeterminate form. So we can actually apply L'Hopital's rule and say that we just take the derivative of both the top and bottom, numerator and denominator. So we have 1 over t, then divided by, so over here this will be, so I'll just rewrite this as a negative exponent, but if you actually solve all that out, you'll get that this is negative 2n minus 2, then divided by t to the 2n plus 3. Okay, so let's rewrite this a little bit better. So 1 over t, flip the reciprocal, so this on the top we'll have t to the negative 2n subtract 3, then denominator is just negative 2n subtract 2. Then if we were to simplify this out a little bit better, they share the same base t, so I'll just write this as a subtraction of the exponent. So on the top we'll have t, then negative 2n subtract 4, then divided by negative 2n minus 2. Then if I take that limit again, or when I write h, that's supposed to be a t approaches 0 plus of our limit, negative 2n minus 4, then divided by negative 2n minus 2, you'll get that this is actually just 0. So therefore, we showed that from now over here, maybe I should write this in black just to make things a little visually easier to then we do this, then we have that this is just 1 over 2n plus 2 multiplied by 0, and therefore the result is that we get 0. Just like I mentioned from the previous video, but it wasn't well explained and I didn't really go into discussion about this whole expression specifically at the evaluation as t equals 0. So yeah, that's pretty cool if you ask me.